Welcome, everyone. My name is Dawn Mullally, CPASS's Communication Manager, and we are delighted to have you attend the CPASS Discovery Seminar Series. CPASS scientists do everything from explore our ocean depths to fly into hurricanes, taking critical measurements, to our heliophysicists modeling coronal mass ejections, and those who unravel the mysteries of the Arctic. And we want to share this with the public, the NCAR-UCAR community, and our many colleagues at universities and agencies across the globe. So just to orient you, we are using Slido so that you can post questions for our speaker at any time during the seminar, and they will be answered after the presentation. Let's see. To submit your questions, just go to the bottom of the broadcast screen. And today, it is my sincere pleasure to introduce you to today's speaker, Dr. Makoto Kelp, who is a NOAA Climate and Global Change Postdoctoral Fellow in the Climate and Earth System Dynamics Group at Stanford University. His research applies data-driven science and machine learning to uncover new perspectives in Earth system processes, especially on the interplay among fires, climate, and society. He is currently focusing on how prescribed fires may limit the extreme air pollution impacts from future wildfires. Makoto received his PhD from Harvard in 2023 and will be starting as an assistant professor at the University of Utah in 2026. Today, Makoto will be speaking on smoke and mirrors, rethinking observations, models, and mitigation of fires. Take it away, Makoto.
Great. Thanks for the intro, Don. Okay, assuming everything is good, I'm going to start. So thanks everyone for coming. And today is something where I'm going to be talking about all the work I've done with wildfires in the past couple of years or so. But first, I think we need a general background timeline of wildfires. And I start by saying that the American West has always burned. Think back to a time in the 1500s. This is pre-Europeans coming onto the scene in North America. We had this routine land management done by indigenous communities in North America. A lot of this is through the use of prescribed fire, which is this low intensity fire where you burn off low-level brush that may accumulate on the forest floor. This is for ecosystem and soil health, kind of managing the soil of the forest for for the sake of crops and also preventing this brush from accumulating and spreading into a large wildfire. And this really has been the case for millennia up until really the turn of the 20th century. The Theodore Roosevelt administration established the Forest Service, U.S. national parks, national forests, where the idea started to become, let's safeguard these kind of natural areas from human development that has been happening in the eastern United States. And, this has been the case where fire suppression started to be the law of the land. In the early 1930s, we had several very severe wildfire seasons burning over 100 million acres over the course of a couple of years. And this really led to the rise of our kind of lovable anti-hero mascot in some ways, Smokey the Bear, where it really was not now enough to stamp out a wildfire as soon as it sprouts up, but we want to actively suppress and prevent them. The saying is only you can prevent forest fires. Then in the 1970s, we have this rise of environmentalism in America, where this led to increased environmental lobbying, which led to direct shutdowns of paper mills and logging companies in the Western US that has really left us without a large-scale infrastructure to remove heavy wooded fuels in the West. And of course, this has culminated in recent wildfire seasons, 2018, 2020, and basically I have to update this slide every year now with all these different fire seasons that we are experiencing. And so obviously I want to say that climate plays a large role in this, right? If you have global warming, which leads to hotter temperatures, leads to more drought and increased fire risk. But there's also kind of this duality of this system where humans also act as a large control on fires in North America. We both suppress and start fires. And right now, the bottom line is that where I'm sitting in Northern California, we're currently burning 10% of what we did before Europeans came on the scene. And we didn't have these mega fires back then. And so, in terms of wildfire risk, obviously the fires themselves pose a lot of harm for ecosystem and human development, but I'm also very interested in smoke. Smoke is largely comprised of PM 2.5 aerosol. PM 2.5 is this kind of aerosol particle that's less than 2.5 microns in diameter and size, and it represents the largest global burden of disease from air pollution. So if you ever read about anything linking air pollution and deaths or cancer incidences, it's most likely from PM 2.5. But PM 2.5 is very interesting in terms of its spatial temporal variability. In terms of space, PM 2.5 can come from a variety of different sources. It can come directly from wildfires, but also desert dust in the Southwest United States. It can be from human industries, on-road transportations or industrial point sources. It can also be chemically formed in the atmosphere itself. PM 2.5 is also very sensitive to meteorological conditions. It can be immediately rained out if there's a convective thunderstorm, or transport, slowly across the country if there's a favorable breeze, kind of like what we're seeing with this wildfire smoke plume in this satellite imagery. In terms of PM 2.5 variability in time, or since the year 2000, and really since the 1990s, average concentrations of PM 2.5 have been going down in America. Air pollution is getting cleaner. We're putting scrubbers in power plants and catalytic converters in cars, and this has really represented a large policy regulatory win for the United States, even to the point where last year we instituted a new annual PM 2.5 standard, going from 12 to 9 micrograms. But as you might have guessed, the growing pollution source of wildfires in the West are starting to undo a lot of the gains in air quality regulations that we've made. This is a really nice and elegant paper by Marshall Burke at Stanford, who I also work with, where we see, if we look at 2016 as this breaking point between when fires have started to increase in their kind of severity over these different fire seasons, we see that PM 2.5 trends in different regions in the United States are starting to reverse, especially in the West, where PM 2.5 is actually increasing, even though we've been pretty effectively regulating it. And there's also potential signal in the Eastern United States as well, where it's starting to level off. And so today's talk is not really about what you already know. I think many of you are familiar or understand that wildfires are a threat to public health and kind of the safety of populations. You know that it's this growing pollution source potentially. It's in the news all the time. What today's talk is to look at the tools and the data that we arrive at these kinds of conclusions, and that there are many different assumptions and biases that may lead to potential overestimations of these impacts. And I want to highlight them kind of throughout this talk. And, I want to say that fires in many ways seem like an incredibly obvious problem, right? You can literally see it from space and satellite imagery. For this image here, you can obviously see something is burning, it's generating smoke, and that smoke can be moving to areas downwind. But capturing these effects in data is actually very difficult, because you might see, some kind of smoke plume here, but that smoke plume is tied to many different kinds of processes, and kind of faithfully representing that in data is actually quite challenging. And today I'll go through each of these boxes and kind of the work that I've done in these different processes related to wildfires and prescribed fires later in the talk. But let's start with emissions, which are really tightly coupled to the land cover and kind of area burned from wildfires. And I argue here that understanding emissions are really at the heart of understanding how fire and smoke are created. Okay. Unfortunately, this is the only box where I don't do any real substantive research, but I think it's important to provide a primer on how we get these fire emissions. And there's two main ways. One is this top-down or fire intensity-based approach. So let's see, we have a fire here, and this top-down refers to a satellite because it's monitoring or measuring this fire from kind of the high up in the atmosphere down to the surface. The satellite has these different satellite bands where you kind of look at the imagery of the ground, and it uses this mid-wave infrared band to measure something called fire radiative power. And this FRP is basically the intensity or the energy coming off of the fire. We kind of measure those radiances, and then we can equate that or relate that to some kind of emissions of smoke from that fire. And how these emissions are calculated is we take the time integration of that FRP kind of radiance measurement over the lifetime of a fire. We multiply by a combustion coefficient, so how burned specific fuel types are under these different conditions. This is largely experimentally derived. It can be from, burning fuels in a chimney or an oven and kind of measuring those in an experimental way. And then multiplying it by an emissions factor. An emissions factor is how many grams of PM 2.5 are produced per kilogram of fuel. And what's really nice about this FRP-based approach is that it's pretty near real time. As soon as the satellite is generating and putting out this data, we can generate these emissions estimates. However, there are limitations, that of the spatial and temporal coverage. There are multiple kinds of satellites that can measure these fire emissions. One is this low Earth orbit satellite. How that works is we have Earth here, and we have a satellite kind of revolving around Earth. It's low Earth orbit, so it can measure pretty close to the surface. The spatial resolution can be on the hundreds of meters scales. But because it's revolving around the Earth, we have 12-hour revisit times. So the temporal sampling is a little coarse. Conversely, you also have these geostationary satellites where the satellite kind of sits at a saddle point from Earth, and it measures continuously a specific area. So as a result, we have much more frequent revisit times from 5 to 15 minutes constantly. But the spatial resolution is coarser as a result. And of course, anything with satellites, you'll have to worry about clouds kind of obscuring the viewing image. Next is we have this bottom-up or burned area approach. How we estimate emissions are to take our emissions factor as I described earlier, and you multiply by these different kinds of components. One is area burned, so this is basically the burn scar of a fire, so how much of that area has been burned by a specific fire. The biomass per area, this can be basically the fuel cover or the land cover, the fuels that are burned. This can be anything from very simple linear classification models to very complicated, complex biogeochemical modeling systems. And finally, the combustion completeness. So this is how much of an area is actually burned, and you can get that from remotely sensed variables such as fuel moisture and vegetation indices. What's nice about this approach is that it's really grounded in the science of what we understand to be important for fires. We take into account environmental variables, land cover, fuel types. But as a result, we also rely on a lot of different output data, which can drive uncertainty and cause kind of our projections to be a little more variable. Because it's kind of a highly curated data set, the outputs are much more delayed as a result. It's not near real time. The bottom line, though, is that most current Earth observation satellites were not really specifically designed for fire monitoring. All of these approaches have been kind of ad hoc, later on designed, that we realize we can use this for monitoring of fires. And this will change in the next decade when we launch specific satellites for wildfire observations. But for right now, we rely on a lot of satellite products that were kind of fashioned after the fact. Okay, so next here is looking at plume rise, but I also don't really work on plume rise, so I repurposed this section for as smoke detection. And really, we have a big problem with smoke detection, and many studies don't even realize it. At the crux of this smoke detection problem is this very pervasive and nice data product coming from NOAA called the Hazard Mapping System, HMS. It's this product that has this real-time identification of smoke in North America. It's used to denote if an area has smoke or it does not have smoke. It's a satellite or smoke product, we call it, because it uses data from a variety of different satellite observations. Here I'm showing you an image of GOES West, where we have a smoke plume emanating from the western United States. How the product is created is that an analyst at NOAA visually identifies the smoke extent using this GOES West imagery. So they see this and they categorize a smoke plume as light, medium, heavy, and manually draws what that looks like on this map. So given this GOES West image, an analyst would produce this exact smoke annotation here for heavy, medium, and light smoke in North America. And of course, there's biases with this potentially because it's hand-drawn, it's only done twice a day, so it can only be done during daytime, and there's also the potential of clouds obscuring the viewing image. But it's a very widely used smoke product that even Google Maps uses to understand air quality and when smoke may be in the air. However, a lot of studies have started using HMS smoke as a proxy for surface smoke presence, but this might not be the right approach. I see so much kind of media coverage saying that smoke from Western wildfires, whether that's in California or kind of the West Coast, is harming air quality on the East Coast. And, that might be correct, but in many ways, a lot of studies have used this HMS product to show that this influence of really large and severe wildfire seasons in the Western US kind of traverse across the country and smoke is seen in the Eastern United States. However, HMS smoke is actually a column measurement. So we don't know where in the atmospheric vertical column that smoke may lie. It may actually be quite aloft. And that's what really inspired this paper that Tina Liu, who's a former CGC fellow herself, worked on. We both advised two undergraduates, Maya Kane and Marie Panday, on this project. And what we did is we took observations from airports that actually track the presence of smoke. So there's an analyst at an airport that reports that today is a smoky day. And this acts as a really nice surface constraint of smoke. And what we do is compare the HMS designations across all these airports and cross-reference them with airport observations of smoke. We find that in the Pacific, which is the West Coast here, and the Intermountain West, so basically the Western United States, observations of airports agree basically with all definitions of HMS smoke. So regardless of light, medium, heavy, the airports say, they all agree within to a certain level of uncertainty. However, the East Coast is actually much different, where if you use this light designation of HMS smoke, which many, many studies do, that this leads to 15 times the number of, 15 times more smoke days than what the airport reports. And so you might say, well, who cares about that? You just say that there's more smoke days, but there isn't. That's not really hurting anyone. The problem is that when you say that there are more smoke days using this light smoke designation, it leads to a more smoke PM that you attribute, when you attribute more smoke PM, you use that to then calculate estimated mortalities. So what are the health effects of that increased smoke PM? And so it really is this kind of downstream a problem where if you have this misclassification of smoke, it can actually be attributing a lot more health impacts in the eastern United States when there actually isn't. Okay, and so as a result, we say that you should not really use this light smoke designation for a binary classification of smoke versus non-smoke. Okay, so other ways that we use to attribute and monitor smoke PM 2.5 is the EPA's monitoring network. And this is really the gold standard of air quality monitoring. This monitoring network was largely deployed, though, in the 1990s. It's very difficult to establish new sites. It costs, $250,000 without the cost of upkeep. So it's very expensive, but the measurements are also of very high quality. And so the 1990s, the ambient air pollution mixture was really dominated from power plants, on-road vehicles and transportation, and also cities. Those were kind of the largest polluting sources, versus today, we're seeing that wildfires are kind of the largest transient source. And so as a result, you see that it's very unequally distributed. You have way more sensors in the east than in the west. There's a priority of the coasts over that of inland areas. And also there are more sensors in urban areas over that of rural ones. So I wanted to ask the question, can we design a new data-driven sensor network for today's air pollution? With today's air pollution being that from wildfires. And so in order to design a data-driven sensor monitoring network, we need good underlying data. And luckily, these machine-learned empirical PM 2.5 data sets have been just exploding in the air pollution literature. How it basically works is you take all these different kinds of covariates and data streams of interest. This can be satellite data, outputs from air quality monitors, or outputs from monitors and air quality models, traffic data, population data, etc. And you feed it into usually a tree-based machine learning regression algorithm that takes these sparse representations of data and combines it into a very dense data product, of which I have daily 1 kilometer snapshots over a 17-year period in the US. Right now, this basically represents the best PM 2.5 empirical data sets that we have. It really outperforms land use regression models that were the standard for the last 15 to 20 years. However, the uncertainties can be large. A lot of studies don't really quantify them very well, because it's pretty difficult to actually kind of quantify the uncertainty of a empirical data product. And I'll talk about this a little bit later. And what I really did not want to do is design a surface observation network just based on averages. I thought that anyone could take this data set, take the average of all these PM 2.5 fields, and place monitors where concentration gradients kind of fall off in space. What I wanted to do is capture very short-lived transient events that have huge impact on pollution that may be averaged out over a long time series. To do that, I use a kind of linear algebra data-driven algorithm called dynamic mode decomposition, which I'll briefly describe here. How it works is I collect my data. This is these 2D snapshots across time. I organize it into a matrix X, where one axis of that matrix is space, latitude, longitude, just squished into one dimension, and the other axis being time. I have that same matrix X, X prime, that is time shifted one time step into the future. And what this DMD approach attempts to do is create this best fit linearly approximating model A that pushes forward these spatial temporal dynamics. And, of course, it's a little bit more complicated than that, involving some singular value decompositions and kind of linear algebra, minutia here. But what this Model A essentially gives us is some kind of background variability of PM 2.5 that we can use to separate from high pollution episodes. And I visualize that here in a sort of calendar figure. But first, before I explain this, I want to acknowledge Samuel Lin, who is a co-author on this paper. He was an undergraduate that I worked with one summer where we published this paper. And so I call this a DMD calendar, and just like any calendar, on the x-axis here, it's just our linear understanding of time, going from 2000 to the end of 2011 for this example. On the y-axis are these different pollution timescales, going from the entirety of this 11-year period all the way down to 1 week. It's very similar to a wavelet style analysis, if those of you are familiar with that. And so if we look at this long-term spatial temporal pattern, we see that there's this spatial map that's produced, and that variability of PM 2.5 is higher in the eastern US than in the West, except for parts of California. This agrees with our kind of long-term understanding of PM 2.5 trends. And so if a pollution episode were to exceed this background or baseline variability, I color it as a red square in this calendar. And you notice that most of these red squares or rectangles fall between 1 week and 1 month. This actually makes a lot of physical sense because the lifetime of PM 2.5 in the atmosphere is around a week. And so there are a bunch of different pollution episodes that I could highlight, but I chose this one. How to read this is that we look on the x-axis. This is an event that happened in the summer of 2007, and it occurred for around 2 months. We look at the accompanying spatial map with the hotspot emanating from Idaho and northern Nevada, and this corresponds exactly with the Murphy Complex fire. It's because this data set, or it's because this approach is built off data that incorporates real world events, that we can pinpoint events in this calendar to pollution episodes that are much greater or much higher above this PM 2.5 background. And what we see is going through each of these events that wildfires are a dominating signal. Okay. Before I explain this map, I want to say that that calendar that I just described to you is essentially a matrix, where on one axis of that matrix is latitude, longitude, just a pixel in space, and the other components or the other dimension being these different pollution time frequencies or episodes. What we can do is take the rows or the points in space of that matrix and find the rows with the greatest signals across all of these pollution timescales, and those are the locations in space that we place a monitor. We find that in the eastern United States, which I don't show you here, the map is actually pretty similar, just with a reduced density in our work. However, the West is a very different story. The EPA has around 15 monitors in the San Joaquin Valley. Our work says that there should be 5 times as many. You know, it's one of the most polluted areas in the United States, frequently exceeding regulatory standards. Similarly, Northern California, wildfire country that I'm sitting in, there's an under-monitored EPA presence, along with areas in Eastern Washington and Idaho as well. And so there's this idea that this data-driven, or you can call it an event-driven monitoring network, is really dominated by wildfires and wildfire smoke, and that there are potential blind spots that we are not capturing based on this kind of framework. Okay. Next is looking at basically a section on how we model air pollution, namely transport and a little bit of chemistry. And that a lot of conventional modeling approaches really fails to capture extreme smoke. But I think this warrants a kind of just a general primer of how we model fire smoke PM 2.5. What are the tools that we use? One is this particle dispersion modeling. You can call it Lagrangian modeling or puff modeling. How it works is you basically take a air parcel over a point in space, and you take data from winds, whether that's kind of convection, advection of transport patterns of winds, and how that box may move and respond to wind patterns. The pros of this approach is that's very easy to use, it's fast, you can use it in a real-time manner, and it's generally first-order accurate because it's just where is that parcel moving based on winds. The cons are that it's very simplified. There's no real chemistry at all, no physics. Because you only look at one box, one kind of box and how that box moves. If boxes cross each other, they don't interact at all. So there's no hope of any kind of nonlinearities in this approach. Next is agency-specific models. It basically takes these particle dispersion models, but also builds on top of it fire-relevant emissions. So it could be if you burn some kind of land cover, it emits this amount of PM 2.5, and then you kind of disperse that PM 2.5 using these dispersion modeling approaches. The pros is that it's more the pros are that it's fire specific. You can use and look at what happens if you burn this kind of emission, or excuse me, this specific land cover. The cons are that it's usually focusing on short-term smoke and pooling. It's just where, if I burn this area or this area burns, where does the smoke eventually end up? Very short-term kind of forecasting. Again, there's no real physics and chemistry, and it's highly dependent on the kind of particle dispersion model that you have and the emissions that you give it. Next are these chemical transport models, which I spent a lot of my PhD running and learning about. The pros are that it has state-of-the-science physics, chemistry, transport. You can have these long-term simulations. It basically represents the state of the understanding of the kind of physical world as we know it. The cons are that it's very complex, it's computationally expensive, you usually need a supercomputer to run these kinds of models, and it's not really observationally constrained. You give it emissions, and then you let the equations of the physical system dictate what happens in the future. And finally are these machine learned and empirical models, which I already kind of touched base on. What's nice about these approaches is that it's completely driven by observations, right? You can have these very different and diverse data streams, and it really represents the most accurate kind of data product for PM 2.5 and smoke that we have. However, the cons are that there's really no science or process-based understanding. It's essentially just interpolating between all these different kinds of data. It's poor at generalizing extremes unless it's just trained on those specific extremes. And there's a lot of input-output uncertainty with that data, which a lot of these are also based on HMS and these biased monitoring locations as well. So you can kind of see that we're building up a bit of intuition as to what is going into these data products. Okay. And so this is a paper led by Minghao Chu and myself, where we wanted to see how chemical transport models behave during these extreme smoke seasons in the Western US. And we find that these models just are really not good right now at tracking and understanding wildfire smoke, which I'll explain why that's the case. But here we look at the chemical transport models GEOS-CPAESS and CMAQ, and we compare it against surface monitor observations of EPA and purple air monitors. Where we see GEOS-CPAESS and CMAQ really heavily overestimate this smoke season month in 2020, whereas the machine learning model here trained on or using out-of-sample predictions are much closer to the observations that we have, which, makes sense because they're trained on those observations. We find that a lot of the overestimations in these chemical transport models are based on plume rise or injection height parameterizations. And that's really more a relic of or a legacy of how these models were initially created. These models were developed in the late 1990s, 2000s. The kind of large focus was understanding chemistry of urban air quality or, kind of ozone events and PM 2.5 from power plants, for example. And a lot of the pollution was just kept within the planetary boundary layer, which acts as kind of a natural cap in the atmosphere over the surface. But we know that fires themselves are so incredibly hot and so explosive that they can immediately penetrate this planetary boundary layer and even potentially go up into the stratosphere. That's where we get these pyrocumulonimbus kind of cloud events. We find that even including or adjusting these emissions injections where only 5% of the emissions are within the planetary boundary layer still massively overestimates PM 2.5 at the surface for these different monitoring locations. And only if we include dynamic injection heights from a separate product that we're able to get closer to the observational record. And I really like this result here. This is basically, we compare against EPA and purple air monitoring locations of where these different models perform best. And we see that these machine learned empirical models perform best in the Western United States, whereas these chemical transport models are actually a bit better, CMAC in the Midwest, for example, and GeoSchem in the East and Southeast. And so, it's a little bit more complicated than that. The details are in the paper, but we essentially look at total PM 2.5. All these three models share the same non-smoke PM 2.5 baselines, and then we add the smoke PM 2.5 on top of that. So this could say that these machine learned models are best in the West, but it could also be kind of an indictment of there actually is not much of these large Western wildfire smoke events that are kind of transporting smoke into these regions. And, in many ways, it takes away kind of the spotlight from problems that the Eastern United States does face. There are a lot of prescribed fires, and there are local wildfires in the Eastern United States. Where HMS we know is not fine scale enough to capture prescribed fire, especially in the Southeast US. And so I say here that potentially based on a lot of these different limitations, modeling wildfire smoke might require more custom or bespoke approaches where we have to blend this idea of this physical system of atmospheric modeling with remote sensing. And that's what we do here in this paper. This is a paper led by Karina Chung, who is a superstar undergraduate. So she's the first author, and I mentored her with Tina Liu. And we created this smart flames kind of smoke tool to look at how smoke affects population exposures in the Western United States. And so what we did is basically take in different components of the atmospheric system that we know are important for smoke exposures. Here we have fire emissions where we use satellite-derived MODIS land cover. We have savanna and temperate forest as the land covers we focus on. We can multiply by these emissions by emission factors to get how much of PM 2.5 is emitted per fuel type. We can then say how much of an area is burned. We can use historic kind of fire seasons from the past to say this is how much of an area is burned, or it can also be user input based. And then we also incorporate the recurrence interval from a separate NASA landfire product, where this is incorporating kind of the inherent fire regimes that we see in the kind of Western land cover. So if an area has not burned in a long time, we say that's an increased risk of it burning. Next is the meteorology. So transport we know is very important. Here we use the adjoint of a chemical transport model to calculate sensitivities or footprints of how smoke PM 2.5 may move around regionally based on the processes of convection, advection, and deposition physics found in this model. And so what we can do is multiply these emissions by this weather sensitivities to then generate population-weighted smoke exposures. But on top of that, we can also look at what happens if we incorporate land management into this framework, where we include historic treatments that reduce fuel loads and emissions based on land manager records that we have, which I'll talk about in the last section as well. What this tool can give us is some kind of risk index. So this is the relative ranking of the highest population weighted smoke exposure. So if an area were to burn that we say is at a high risk of burning, let's rank if those areas were to burn, what is the highest risk of creating the most smoke for populations? We can also compare this to a post-intervention baseline if we were to have done some kind of land management to prevent that. And the idea or the spirit of this tool is to assess smoke exposure across the West and target areas where prescribed fires would yield the greatest benefit to air quality downwind. What's nice is that this tool is online and available right now. You can find it on my website. You can find it on Tina Lou's website. And all of those parameters that I described are tunable by the user. So if you think the emission factor should be higher or lower, you can change that. And I wanted to end this section with a kind of science result we found is that using this tool, we find that the highest smoke risk to downwind populations are really found within this wildland-urban interface in regions near major cities in Northern California, being San Francisco, San Jose, and Sacramento. This wildland-urban interface, or WUI region, we call it, is the area kind of between urban areas and remote areas, kind of where humans are starting to encroach into areas with heavily kind of forested land cover that might be at risk of burning. And so, you might think, well, this is an obvious finding, right? Of course, the areas with the highest population smoke risk are areas with populations. But in many ways, this is not a foregone conclusion. Especially, we see it in a lot of fire climate relative or related studies that areas with heavy fuel loads and the highest risk of drought due to kind of climate change are not in the WUI. They're kind of far off in the Sierras or in areas where it's more remote that can generate a lot more smoke. But we find here that still prioritizing the WUI is the largest kind of important area for kind of managing smoke exposure. And this is my last section here. I'm not going to talk about exposure and impacts as much, but I'll talk about mitigation, which is largely through the use of prescribed burning. And, in America right now, prescribed fire, controlled burning is a complete socio-political nightmare. This is a really nice figure by Kirk Baker, where the size of the circle is area burned by fire, and the color of the circle is by different fire types. We see that in the eastern United States, prescribed fire is a very common land management technique. They are done through, or prescribed burning is used to clear off sugarcane areas in Florida, to clear off forest floors in Georgia for hunting. There's a ton in the prairie lands. This is pretty ingrained in American culture to the point where even these were written about in the Little House on the Prairie, those kind of Laura Ingalls Wilder books from, over 100 years ago. However, prescribed burning is very much a boutique application in the Western US, where out-of-control wildfires dominate the area burned. In California, there is a proposed expansion of prescribed burning to burn 1 million acres per year as a kind of mitigation strategy to prevent future wildfires. But we really don't know the trade-offs of what that entails. We might be trading off smoke that is experienced in cities for weeks out of the year to generating smoke in rural or vulnerable communities kind of year round. And we don't even know if it'll prevent future wildfires as well. And so to look at these kind of dynamics over time, this is a paper I published in 2023, where the pixelated base map are outputs from air quality models that I've described to you before for September of this 2020 wildfire season. The black dots represent large prescribed burns, large being over 1,000 acres or around 4 kilometers squared, over the course of a 5-year period preceding this September 2020 month. And these are satellite-derived locations where we see that there's a mismatch between where these aggressive treatments have been done and where smoke was largest during this really extreme wildfire season. But it really varies state by state. You have kind of routine and aggressive land management policy in Arizona and New Mexico in these Tonto and Apache Sitgreaves National Forests. In Central Oregon, this is largely agricultural burning on privately owned lands. Whereas Northern California, basically wildfire country, we only had 7 prescribed fires of this magnitude. And maybe those of you who are familiar with prescribed burning might say, that doesn't sound right. 7 fires over a course of 5 years. I definitely know there's more than 7 fires. You'd be right. In fact, even over a 3-year preceding period, 2018 to 2020, there's almost 10,000 prescribed burns in California or Northern California, but they're just very small in size. Instead of a satellite-derived product, this is from on-the-ground land managers who do these prescribed burns and different operations. And we see that when we filter by acreage, that even exceeding 500 acres or around 2 kilometers squared, less than 1% of all treatments are of this size. And so, maybe doing many, many small burns is not enough to kind of undo the legacy of 100 years of fire suppression that we've had in America. We see that these prescribed fires are not occurring at very large scales, 4 kilometers squared, which, aren't really very large compared to how much area an actual wildfire in the West burns. There are many small applications, and I wanted to ask the questions, do these applications actually work in preventing or buffering against fire impacts? And again, there's this large policy focus on the WUI, which I described to you in Karina's paper. And so this is the last project that I'll talk to you about today. And I wanted to see what has been the effect of having done these prescribed fires when these treated areas later reburn in a wildfire. And to do this, we need very high resolution data. Luckily, we have a lot of satellite data to work with. So within a wildfire burn perimeter, we have the locations of these prescribed fire or land management treatments. We also have satellite burn severity data. This is DNBR, or the difference in the normalized burn ratio. It's pretty much how burned an area is pre-post fire. We also have for California a nice emissions inventory at high resolution for PM 2.5 that basically translates burn severity data into PM 2.5 emissions using kind of emission factors. And this is a product put out by UC Merced. In addition to other covariates, high resolution covariates that are relevant for fire management, such as land cover and elevation. And this approach here, I took a little bit of a different kind of path and used kind of econometrics or causal inference-based analyses, where we created this experiment where we know the area that is treated by the United States Forest Service or by CAL FIRE, that's kind of designated in this blue area, because they report the acres they treated. And then we construct a control buffer of an area equal in kind of acreage directly outside of that treatment zone. And what we can do is compare all of these control areas to these treated areas. And we fix the effects of time invariant aspects of the data, such as elevation and land cover, so we can kind of see the effect of these treatments across all these different landscapes in the Western US. And the major finding is that these pooled estimates across the West show that having done these treatments relative to controls, that burn severity was statistically significantly reduced by 16%, and that PM 2.5 emissions in California were reduced by 101 kilograms per acres. And so, and before starting this project, I thought we would get a null result. I thought that there's no way that these little tiny treatments, I bet even if they're engulfed in a severe wildfire, they would make no difference. But we see that systematically they are reducing and buffering these effects against an area being more severely burned and emitting more PM 2.5. And so looking at kind of more metadata associated with this analysis, if we divide this into different treatment types, we find that doing prescribed burning statistically significantly reduces the risk of burn severity, whereas performing mechanical thinning, which is not using fire, it's more using heavy machinery, chainsaws to kind of trim back forests, were not significant. We didn't find this to be significant for the PM 2.5 values, but this is because this PM 2.5 data product is essentially this burn severity, fine granularity data, which then you apply emission factors on top of it, and it kind of smooths it quite a bit compared to these more high resolution burn data. And one really interesting finding we see is that the treatments done outside of the wildland-urban interface, away from populations, are more effective in reducing burn severity and PM 2.5 emissions, whereas those treatments done inside the wildland-urban interface have been ineffective. And if we disaggregate by these different kinds of treatments and WUI designations, we find that prescribed fire is really a big driver of reducing burn severity outside of the WUI. This is because our hypothesis is that when these fire managers are doing these kinds of burns, that there are heightened considerations of you don't want smoke to come into a community, you don't want that prescribed fire to escape and affect that community, so they don't do it as completely as they can. And this is my last slide here, where I want to acknowledge that prescribed fires themselves emit smoke. So, smoke from any source is bad and harmful to human health. But using a emissions inventory from Claire Scholart, we find that looking at these two large fires, the Creek and Slater fires, that the prescribed fire emissions of having done those treatments before the wildfire emitted 144 tons of PM. However, having done those treatments and using our estimates, we find that we save 630 tons and that the end result is that we have a net savings of smoke PM 2.5. However, you notice that this the axis here is the percent of wildfire emissions, and that although there is a net kind of benefit of having done these prescribed burns, that it's still even much less than 1% of the entire smoke budget from these wildfires. And so, I leave my final takeaways here. And the one I want to kind of specifically say again is that the last couple papers I show is that we find that WUI treatments are critical for reducing smoke exposure, but they are also found to be less effective in practice. So I think that's a very interesting takeaway given how much of a large policy focus we see on the wildland-urban interface. But thank you so much for your attention.
Thank you, Makoto. That was a very, very interesting talk, and we truly appreciate it. Now we're going to begin the Q&A portion of today's seminar. I'd like to direct everyone's attention to the Slido on your broadcast screen, so please ask questions. And while you are doing that, I would like to invite you to check out our webpage, which is cpaess.ucar.edu, discovery seminars for our upcoming seminars. Our next one is scheduled for Wednesday, May 21st at 11 a.m. Mountain Standard Time with Dr. Robert Yarlim, a NASA Jack Eddy postdoctoral fellow. And we also invite you, and I already had somebody reach out to me during your talk, Makoto. We also invite you to find this talk and past talks on CPAESS's YouTube channel. So that will be up within the week. Please ask any questions if anybody has any, but I do have a couple. This was very interesting. This was a great talk. And what would you, given the information that you have, kind of your research has discovered, what changes would you like to make in prescribed burning, particularly in the West? And I know it's a very big question.
Yeah, I mean, I think prescribed burning in the West is a very difficult it's almost a political kind of problem, similar to climate change, right? Where states determine how aggressive they are with prescribed burning management. So we see in the desert Southwest, like Arizona, New Mexico, they do this all the time. They burn thousands of acres and it's pretty well managed. Whereas in the Western US, you have, very potential rocky terrain, you have high population centers, so the risk is very heightened. And there is a lot of bureaucracy in kind of planning this. So, for example, at this point, maybe a year and a half ago, there was a prescribed fire done for 500 acres, so around 2 kilometers squared in Sacramento. That took over 50 people, and you have to get the burn permits. The planning of that prescribed fire itself actually takes years because you have to submit the permits. You have to go through this kind of system through the U.S. government. It's through the National Environmental Policy Act, which then you have to have community input, which communities, a lot of them do not want this, right? Fire seasons are already very long, and now you want to burn things on purpose and generate smoke. So in many ways, I think communicating that to the general public is actually one of the most important issues. We see that kind of climate change education or here prescribed fire education can actually play a large role in altering people's perceptions of, yeah, we know we need to do this. The Eastern United States, they actually want these prescribed burns so they can go hunting. And so, then things don't catch on fire later, or it's good for the crops. We don't really have that kind of educational or cultural infrastructure in the West right now.
Excellent. Um, this is maybe a peculiar question, but you sparked my interest at the beginning of your talk. Do you have, and I don't know that it would be relevant today, but do you have any anecdotal information about pre-colonial times and the prescribed burning that went on after that? And then we have other questions.
Yeah,
So
no, that's a great question. I mean, this was very pervasive in kind of pre-European intervention or colonization, where we see kind of records from indigenous communities that, for example, the Central Valley was filled with smoke all the time. Right now, we're burning 10% of what we were doing before Europeans came. So that means, an additional 90% we're not doing. And so generating and creating smoke was a very kind of common part of lifestyle, very common element of land management. But, there's still ongoing research showing that the smoke, there's less smoke emanating from prescribed burns than wildfires. It depends the severity of the fire, how does that affect the concentrations of PM 2.5 that places may experience. But in terms of kind of indigenous records, we see that this was a very, very common land management technique.
excellent. And then we have a question here from Tim. Interesting talk. Do your results suggest specific fuel types that should be targeted during prescribed burns to reduce burn severity?
Yeah, I mean, the findings that we have there are not super specific to a certain type of land cover. So we use pretty coarse categories. So like savanna, savanna can be grasslands. It can be any kind of subcategory of grass. We don't know specifically of what kind of grass is most amenable or what we should target the most. Also, another category we used is basically forests. What does that look like for broad needle leaf or, all these different kinds of species and categories? I'm not sure. So generally, of largest interest are savanna or grasslands and forests. And we see that forests, generate more smoke than grasslands, but grasslands can burn easier. So, that's not really answering your questions, but I think that's kind of a next step once we kind of get more and more data, which this is actually a fairly data poor problem. A lot of this data is not public, and you have to kind of work with agencies, and we have co-authors from the United States Forest Service who help us kind of get that important information.
Great. I'm taking over. Thank you. I think that's the end of our questions. So we will just say thank you and what a great presentation. And we will see everyone back here next month on Wednesday, May 21st, same time, same place. Thank
Thanks
you,
so much.
everybody.